And we talked about how that hydraulic system uses the distance principle. We talked about we had a small piston and a big piston. Which piston had to travel the furthest? The smaller the piston, the further it traveled. Okay, the bigger the piston, the less it traveled, because the volume that moved on either side was exactly the same, but because when your area is bigger, its height isn't going to change as much, or depth, depending upon how you want to look at it. Anything else that we talked about you guys can remember? Maybe looking back in your notes right now would be a good idea. What do you say? Buoyancy. Okay. What is essentially buoyancy? What was that? Like floating or not. I mean, I know the why behind it is conceptual, but if I say that it's positively buoyant, what does that mean? It floats, okay. Negatively buoyant means? Sink. And if it's neutrally buoyant, wherever I put it in the column of the fluid, it's just going to what? It's going to stay there, right? I know that's kind of weird to think about, but yes, it is possible. Okay? They try to make submarines neutrally buoyant so that the engine of the submarine that propels the submarine through water doesn't have to fight the fact that it falls or it rises. Does that make sense? Because if the submarine was so huge and so dense, and as soon as it plopped in the water, it just fell, that wouldn't make a whole lot of sense, right? Or if you put a submarine in water and it just rose, that wouldn't make a whole lot of sense either. So when they make submarines, okay, they try to make them as neutrally or close to neutrally buoyant as it possibly can, so that when the propeller kicks in or whatever it is that causes the submarine to move through the water, it's not fighting the fact that it wants to rise or it wants to fall. Okay? We talked about how when you're in a fluid, what happens to your weight? It gets lighter because when you displace the fluid, okay, the amount of fluid that you displace, the weight of that, or the force of that, pushes back up on you, lowering your gravitational force or weight. Okay? What else? Anything else? What was pressure? What's the equation for pressure? What are the applications of it? Yeah, force over an area, and we said that if you increase the area, does the pressure go up or go down? It goes down, right? If I take and apply a force over a much larger area, it waters down that area, no pun intended. Right? You guys understand when I say water it down, right? It's not as strong. Because you're taking that force and you're applying it over a larger area. But if I can reduce the area, all that force is on one little area, you're gonna feel a much higher pressure. Okay? What's the unit for pressure? What? Pascal, PA. Okay, there's lots of other pressure units, but that's the main one that we have talked about. All right. 3 slides today. First one's the longest. We're going to watch a short YouTube video.
Yay.
And the YouTube video is actually an AP Physics video, so we're gonna treat you guys like advanced seniors today. How about that?
Oh, yay.
It's actually he does a pretty good job of explaining the idea. It's some pretty cool visuals that I don't possess, so. Okay, first bullet there. Mari, read it. Okay, so a fluid's ability to move or flow is primarily due to pressure. And you may have heard this before in the terms of like temperature always goes from high temperature to low temperature, hot to cold. Same idea for pressure or for fluids flowing. They always go from a region of high pressure to a region of low pressure. An example of this would be like water or something in a hose. Okay, inside the hose, there's high pressure. And at the opening of the hose, okay, so inside the hose there's high pressure because of all that fluid built up in there. Okay, and then right at the entrance of the hose, or exit I suppose you could say of the hose, what is the only pressure there? Air pressure. Air pressure is significantly lower than the pressure within the hose. That's why when you turn on the water, it goes from high pressure to low pressure, and the low pressure is outside due to the fact that the only pressure exerted back this direction is air pressure, which is relatively weak, right? We're not feeling an immense amount of pressure when we walk around due to the air pressure, right? We feel a little bit of ear popping when we move up a long ways in the atmosphere, okay? So there's not a lot of pressure in the air. Now, it says the rate of flow is proportional to the difference in the pressure. If you have great pressure differences, the faster it will flow. Okay, and we're going to talk about another principle here in a little bit, which kind of puts some of this stuff together. Other factors that affect pipe size, area of the pipe, big pipe, little pipe. We'll talk about that in a little bit when we look at the video. Density of the fluid. Okay, we'll talk about that in the video as well. And the viscosity. You guys remember? Do you guys know what viscosity? We talked about viscosity, right? Liquid, subliquid. And the reason how viscosity plays an important fact has to do with friction. Okay, and its ability to flow. Okay, so I want you to get this next slide in. I'm going to show you a video. Bernoulli's principle. There's a lot of principles in this particular chapter. We got Pascal's principle. We have Bernoulli's principle. We have one other one, don't we? No. What was that? Boyle's law? That's later. I thought there was one more before. Maybe it wasn't a principle. Maybe it was just.
Oh,
Archimedes, yep. Was Archimedes a principle though, or was it just? Now, this equation looks pretty complicated. And the honest answer to it is yes, it is. You guys know what P stands for? You guys should remember what KE stands for. What this basically is energy conservation. For a particular fluid inside an enclosed container, if I have position A and position B, the energy between position A at position A and at position B should be equivalent. They might be in different energy forms, but the overall energy should always be conserved because we cannot create or destroy what? Energy. So since we can't create or destroy energy, the sum of all the energy at one location should equal the sum of the energy at another location. So this could go up and this could go up. This is probably going to go down. And I can change, some variables might go up, but the other variables are going to go down proportionally so that your energy is still conserved. And we'll talk about this as we progress here. Okay? We're going to talk about differences in the area of a pipe. We're going to talk about how the height of the pipe, why when you take a shower on the first level versus the second level, why there's different water pressures, things like that. So, let's watch a video. And please stop me if there's something in the video that you're confused about. It is a video for AP Physics, but I don't think it's outside of your ability to understand. And I'm going to try to stop it, break it down, talk about it, make sure we understand what's going on. For copyright purposes, I'm going to move that.
Physics Essentials Video 88 is on Bernoulli's equation. And a great application of this is the reason why docks aren't solid, why they're made of pilings so water can flow underneath it. If you were to have a big boat like this, we're looking at it from above, come into a dock, if it was solid, it would force all the water out of the way. And that fluid, as it's moving faster, would have a lower pressure. There'd be a higher pressure on the outside of the boat, which would slam it up against the dock. And so Bernoulli's equation is really conservation of energy inside a fluid. And to solve most of the problems, you'll first have to understand how the continuity equation works. Continuity equation is equal to A1 times V1 equals A2 times V2, where A1 is the cross-sectional area, and V1 is going to be the velocity. So if we look at a pipe like this, and so fluid is flowing through it from left to right, in two different points, A1 is going to be the cross-sectional area, so the area of this pipe here, and A2 is going to be the area over here.
Does that make sense so far? Okay, you're saying point 1, point 2, one has a higher area than point 2. Does that make sense? Nothing crazy. Have I showed you the continuity equation? No. But it's not an overly difficult equation. You'll see this.
Attention, zoology class needs to be dismissed at this time to leave for their
And so if you look at a velocity, that's what V1 stands for. Since we have a large cross-sectional area here, we're going to have a relatively low velocity. And then as we move to the right, since we're decreasing that area, we're going to have a high velocity. And so if you know the velocity at any point in the pipe, since that whole fluid's moving, if you know the cross-sectional area anywhere else, you're going to be able to figure out the velocity there. An application of this, if you've ever had a hose, as water comes out of it, it's got a large cross-sectional area. If you put your thumb in front of it, what are we doing? We're decreasing the cross-sectional area. What happens to the velocity? It increases.
Everybody catch that? You ever, if you just have a hose and you turn on your your water, the water just kind of flows out fairly slowly, right? Okay? Because it can go out the whole area, right? When you put your thumb over it, you're decreasing the area that it can come out, correct? Okay? So as the area gets smaller, the velocity goes up. So that's why it shoots out with more force, because you've decreased the area. Same amount of water's got to pass through, so it has to go faster. Does that make sense? That's really the continuity equation. That it's the purpose of that is that when you have a large area, velocity is what? Less. When you have a small area, velocity is more. Now that's really important to understand Bernoulli's equation, so that's why he first started talking about that.
Now, if we look at Bernoulli's equation, it's somewhat scary when you see it the first time. It looks like this.
Now, does that look like the equation that I put on the board? No, this is the more difficult format of it, but you'll find out that those other things, he'll show you in a sec, that they just represent the same thing that I showed you.
So this is going to be Bernoulli's equation. And it's frightening to look at, but what we've really added here are simply two things. We've added y, which is going to be the height of the pipe, because that's the potential energy. And then the other thing we've added is a rho, which is going to be the density of the fluid, because those can affect the amount of energy that we have. And so if we break apart this equation, we've also got 1 on the left side and 2 on the right side. If we look at this first one, P1 stands for the pressure. So inside the fluid itself, how much is that fluid pushing in on a point inside the fluid itself? So that's going to be the pressure energy. We then have this, rho g y1. Now that seems confusing, but let me kind of write it out a different way. If we were to, instead of write rho or density, if I were to say the mass, this is g, gravitational energy, or gravitational field strength. And then if we were to look at y, if I wrote h there, or the height, what is mgh? You know that. That's just the potential energy of the fluid.
You guys remember that equation? Yeah. Gravitational potential energy, what was the equation? mgh, right? Mass times the gravitational acceleration times the height. What this is, rho is just density. It's very similar to mass. The reason why they use density is because fluids can be more dense or less dense. Okay? G is gravitational, and the y is your vertical coordinate referring to your height. Okay? So I know this looks goofy, but what could we really just replace with that? Potential energy. Okay? So, what you doing, Mari? Mari! Sit up. Thanks.
And so that second
Eyes up here, Mari.
bit of this equation is going to be the potential energy of the fluid. And then if we write this next one, what is 1/2 mv squared? That'd be kinetic energy, but we're writing density since we're dealing with a fluid. So
Did you catch that? 1/2 mv squared. Have we seen that equation before? Mass times velocity squared. Which equation was that? Kinetic energy, right?
so that's going to be the kinetic
Don't
energy.
be
And so those
scared
are
by that
fluid
equation. It's the
energy
same one
on the
that
left side of
I
that
just
pipe.
showed you
It's the
a second
pressure
ago.
of the fluid. It's the potential energy, how far it is in relation to gravity, and then the last is going to be the speed of that fluid. And since this is the conservation of energy, in these 2 points of the pipe, since we know the energy over here, and we know it's going to be an equal amount of energy over here, we can solve some pretty complex problems. So for example, if we were to look at this pipe right here, on both sides, they both have the same height, or the same y value. So I've taken those out of this equation. And so where's the velocity going to be faster? It's going to be faster on the right side of the pipe. So we're going to have a faster velocity on the right side, slower velocity on the left side. So what has to be our pressure on the right side? Well, to make it equal on either side, conservation of energy, we're going to have a lower pressure. So
Everybody understand why he canceled out the potential energy portion? Why did he cancel out the potential energy portion? Both the same one. Height. So the center of this area is at the same height as the center of this area. So those fluids have the same potential energy. If the number here and the number here are the exact same number, if you mathematically solve, they would just do what to each other? Cancel each other out. So that's why he got rid of those, just in case you weren't following.
just like in my example of the ship, if the fluid is moving fast, then it's going to have a lower pressure. And so let's start with the continuity equation, which is simple. We've got a Pt2 simulation. You can see as the fluid's moving, it's moving faster on the right. And so if we use a flux meter, on the left side, the cross-sectional area is 10 meters squared, and the speed is going to be 0.5 meters per second. So that would be my A1 times my B1. If I move over to the right side, now my cross-sectional area is 1. What's my velocity? 5 meters per second. And so I can just solve for the one I don't know, and I can figure that out. If we were to just change the pipe, now the cross-sectional area is 5 meters squared. What's going to be my speed? It's simply going to be 1 meters per second. And so continuity equation is very, very simple. If we were to apply Bernoulli's equation, what we're really adding to it is the density of the fluid and the height of the fluid. And so let me give you a thought experiment. Let's say I were to take a half a gallon of milk, and I were to pop 3 holes in it and quickly put tape over it like that. So the whole thing is filled up with a fluid. And then I were to simply pull the tape off the side. So what are we going to get? Streams of milk coming out of the carton. But do you think those streams would look like this, or like that?
Think about it. I know we haven't talked a ton about this, but just do your best, give your best guess, and maybe see if you can come up with a why. Everybody, what do you think?
DC, because like there's more pressure in the deep.
Ooh, okay. All right. Anybody else have anything to add there? Anybody? It is C. The answer is C. Let's talk about this. Okay? We said that we have pressure, potential energy, kinetic energy, okay, in all of these locations. So the energy at all of these points should be equal, but are there pressure, potential energy, and kinetic energy going to be equal at all those points? Now, okay, the first one that we probably the easiest to look at is the potential energy. What's true about the potential energy between these ones? Which one has the most potential energy? This should be an easy one, guys. Why? Height. Right? What is potential energy most determined by? Height. So this has the highest potential energy. This has the lowest potential energy. But remember, the total energy should be the same at all those locations. Okay? If the potential energy is lowest here, then its kinetic energy and its pressure should probably be higher. Okay? So if the kinetic energy and pressure are higher, one is going to shoot out faster. That's why it's going to cover more distance on the x-axis. Does that make sense? Because the potential energy is high here, it's going to have a low kinetic energy and a low pressure. That's why it doesn't shoot out very fast and it just kind of drops due to gravity. Does that make sense? Bernoulli's principle. Okay? Now, his explanation of this is wrong. So, we're going to...
If you were to look at it from the side, which is going to be the correct understanding both sides of the pipe, where is the potential energy greater? It really helps you understand how Bernoulli's equation works. And so it's written like this. Left side, remember, it's going to be the pressure energy, the potential energy, and then the kinetic energy. And they're going to balance, so it's the conservation of energy. If we know what's on the left side, we can solve kind of for what's on the right side. So let's try to solve a problem using Bernoulli's equation. So I've got a pipe.
Let's stop here. Okay? Let's say this is a point, and this is a point. Everyone follow me? Okay? Which point, A or B, has the highest potential energy? B, because of what? Height, okay? Then, at point A or B, which one has the, which one's probably moving faster? what do we know? We know that if your cross-sectional area is small, you move faster. Okay, so this has high potential energy, high kinetic energy, so it probably has low pressure, which typically we said with a small cross-sectional area, the pressure is small, right? And if this has low potential energy or lower and lower velocity, kinetic energy, then it probably has high pressure. But if we put in those numbers, the sum of all those numbers should what? Equal conservation of energy. Okay?
Height. I've got a left side and a right side. On the left side, you can see the velocity is lower. I'm giving you the pressure on the left side, but what we're going to solve for is the pressure on the right side. So let's go through this equation. On the left side, I'm giving you the pressure. On the right side, we don't know what that pressure is. On the left side, do we have less or more potential energy in the pipe on the left side than we would on the right side? Well, the density of the fluid, since it's water, is going to be the same on both sides. And since the pipe on the right side is going to have a higher height, it's going to have a higher potential energy on the right side. What about this? Are we going to have a higher kinetic energy on the right side or the left side? Since it's going faster on the right side, on the right side it's around 87 kilopascals, so it's around 90 kilopascals. And so we can use Bernoulli's equation not only to calculate, but we can use it to just analyze confusing situations when we have a fluid. So how does a curveball work? When you throw a curveball, it should drop. So as the pitcher tries to, or rather as the batter tries to hit it, it's going to drop right at the end. And so how does that work? How does a curveball work using the fluid of air? So as you throw a ball, let's say it's not spinning, as it's moving through the air, the fluid of the air is going to move around it. But since it's not spinning, the velocity on the top and the bottom is going to be exactly the same. But when you throw a curveball, you start spinning it. So it's spinning like this, and it generates a wind on the top, which counteracts the wind that's already coming in, and so it decreases the speed of the wind on the top. But on the bottom, since the wind over the ball and now the wind generated by the spin of the ball are both going in the same direction, the fluid on the bottom is going to be going faster.
Okay, everybody see that. It's spinning, causing more air to go underneath the ball, or the air underneath the ball go faster, okay? Then on the top of the ball, and when we said that when it's moving faster here, what's true about the pressure? Lower, right? Faster moving usually means lower pressure. Not always, but usually. So the pressure is lower pushing up. Here the particles are moving slower, which means the pressure here is what? Higher. So you have low pressure pushing up, high pressure pushing down, and that's why the curveball will what? Drop. That makes sense? Okay. That's probably good for this. Let's get to the last slide. Wanda effect. All right, there you go. Someone's coat. Yeah, but I couldn't figure out how to do that on my Word document. Okay, and then once you get this in, turn to 166 in your book. Actually, there are some uses to the quanta effect, and one of them is how the new leaf guards work. I don't know if you guys know what I'm talking about. Gutters that try to keep, we've been trying for the longest time to try to get it so that water gets into the gutters, but what does not? Leaves. And A lot of the old school ones, they just had like a mesh thing over, which a lot of times those things would fall off and all sorts of stuff, and there'd be problems, like if the leaves would block the mesh and the water would just fly right off the gutter. And there was not a lot of good applications for this. Okay? Then they used the quanta effect to try to fix this problem. And if you look at the bottom of page 166, is everybody there? Okay? What they have is those gutter guards are really just a curved metal surface that curves back towards into. And so what the water will do is it'll run along that metal, and it'll, because it's attracted to the metal, it will curve along the metal and curve in, but the leaves will just what? Slide right off. And so, let me kind of show you. It's pretty simple, but you should see that if I go like this and put this on, you should see how it's curving, and does everybody see it curving along the surface of this? It's not shooting straight off, right? It's curving, coming off underneath because it's attracted to the glass. And so those people who came up with the leaf guards used this idea to curve water into the gutter, but obviously the leaf is not a fluid, so it's not going to curve into the gutter, it's going to slide right off. Pretty cool. We're done.
Leave it there.